Thanks, Yumi. Hi, my name is Josh Peak, and I will be talking about all of astronomy and all of machine learning. So I hope you brought food. Um, I hail from Space Telescope Science Institute, where I'm the head of data science. And a lot of this work is with my collaborators, John Wu and Rick White in particular. John, who's here, so I'll be showing his work quite a bit, as well as my own. I guess I just wanted to take a moment to say that there's a great quote. There are more fish in that sea than were ever drawn from it. And it's a quote by Cecilia Payne-Gaposchkin, and she's speaking of the Harvard Plate Archives. So this idea that we're going to be looking for these gems in our large data sets goes back more than 100 years, and also was started by the women who were the original computers that were working on these projects. So I'd just like to give a shout out to her and her squad. Okay, so what is machine learning anyway? Well, I think this is a good quote by Randall Munroe. This is your machine learning system. Yeah, you pour the data in this big pile of linear algebra and collect answers on the other side. What if the answers are wrong? Well, you just keep stirring. And I don't think that's necessarily wrong, but the key idea here is that we need to be sensitive to what we're doing when we're using machine learning, and to think about how principled what we're doing is, and whether we need to be really careful around those principles. Another quote I really like, just to start off a little bit silly, is I saw the best minds of my generation solve deep, long-standing problems in AI in order to serve better ads, which is a reference to the poem Howl. I think the key point here is that machine learning was not built for us. It was not built for astronomy. It was built to sell better ads. You'll hear me say a number of times during this talk, I'm not opposed to selling better ads or markets or anything else, but that's not what we're trying to do in this room. There's a lot of value in the unmarketability of astronomical data. And so I just want to point out that we have to be careful when we use machine learning tools. So it took me about 8 years to come up with the answer to the question, what is machine learning in the astronomy context? And this is my argument. Machine learning is statistics, but where every parameter is a nuisance parameter. You're fitting to the data, just like you would in statistics, but you don't care about the parameters of the fit. Okay, that may not be many other people have arguments about machine learning about, computer science and speed and efficiency and all sorts of other things. There's lots of other cultural reasons we call it something else. But this is what I think is different for this community and something to keep pretty central and in mind. So I'll give you a nice example. This comes from Jake Vanderplas and the IVSIC textbook on machine learning, which I really appreciate. And what's great is they made all of this available so you could run the code yourself. So I highly recommend that approach to figures. On the left side, you see a straight line regression to the apparent magnitude versus redshift of a bunch of supernovae. And then on the right side, you see a fourth degree polynomial regression. This is statistics because we're fitting to the data, and the slope of the data, the slope or the various parameters of those fits are the things you're interested in, right? You probably wouldn't use a fourth degree polynomial. If you're a cosmologist in the room, you're screaming in your head, actually, there's a specific function that I would use to fit this. I'm not a cosmologist, but there's some function that probably has the parameters you're really interested in, and then you can measure their errors and you can measure their covariance and everything else you want to know, and understand how they're sensitive to the data. This mathematically, are we gonna do this? This mathematically, a lasso regression, is basically the same. It's a fit, but what you're fitting is a bunch of Gaussians on the bottom on pistons, and you could have a million of them in here. And because you're using lasso regression, you can fit as many of these parameters as you want. But it's garbage, right? It might create an amazing machine. So the machine might know how this thing works. You can now give this machine a redshift and it will give you an apparent magnitude and you're good to go. But that's not what you were trying to do, right? You're trying to learn about the structure of the universe. And so please, we invented inference. We invented Bayesian inference and all different kinds of inference, statistical inference. Please use that if you can, if you're really trying to measure those parameters. But many times all we want is a machine. So I'll come back to this theme and I'll use this little light bulb emoji and I'll use this robot emoji. This talk is like half sass, half emoji and half memes, and that's why it's too long. Okay. So here's the structure of the talk. What is ML in astronomy? I feel like I just did that. I'm going to talk about supervised versus unsupervised machine learning, and then I'm going to talk about it in the context of astronomy. And I'm going to try to go quickly, but clearly. Okay, so here we are, supervised versus unsupervised. So I just showed you, what this might look like. So we call this regression. Statistics went through and took all of the words we already had and gave them new names. Then we went through and gave them new names, and then machine learning came along and did it all over again. So everything, there's lots of synonyms here. So regression is fitting, and that's an example of it here. So supervised here means you have some label. And in this case, the label would be the independent, the y-axis here, so the apparent magnitude. And so you're basically saying, I'm going to remove some of these data, I'm going to fit or regress on these data, and then I'm going to check by putting my parameters back. Okay. In a machine learning context, you can't assume many of the things you assume in a pure statistics context, and so this process of blinding and checking is how we do this. So that's a regression problem where what you're asking is some independent variable. Very similar to that as a classification problem. So I'll show you an example from my own work here. We were interested in looking at some blue horizontal branch stars. Blue horizontal branch stars are bright UV objects of some known distance because they're sort of standard candles. And we were using them to look at the interstellar medium, which is still very important. But the problem is we didn't have a good catalog of them. There was not at the time a large catalog of blue horizontal branch stars. And so what we did was we took the spectroscopically identified catalog, we figured out where it was in color space, and then we essentially just did a very simple KNN classification, which allowed us to figure out which of our targets, which of these zillions and zillions of objects that were in these beautiful surveys that NOIR among others holds, and then figure out where the blue horizontal branch stars are, and then pointed Hubble at them, and all of them were blue horizontal branch stars, I'm happy to say. And we got these very nice results about the very important interstellar medium. We could have taken a really advanced model of stellar atmospheres, and we could have taken all of the filters, and we could have processed everything through, and we could have identified exactly which stars had which masses and which stage of their evolution and so forth, and we could have picked the blue horizontal branch out of there. So we would have had all of these parameters, and they would have picked up all of these parameters, and we would have dropped them in the trash, because I don't actually care about blue horizontal branch stars. Maybe you do, and in that case, you should be using statistics. But in my case, I'm using machine learning because I just want to get the answer, is this a blue horizontal branch star? So I could go study the important thing, the interstellar medium. Okay. Had to get that off my chest. All my other talks are about the interstellar medium. So unsupervised learning. One of the things that we do in unsupervised learning, this is where we don't have labels. Okay, this is where we just have the data, and we're trying to learn effectively the space in which the data sits. So you have this high dimensional space, and you have some manifold, okay, some surface. You can think of it as a 2D surface, but it's probably a 11 billion dimensional surface in which the data sits. And so here, you might want to reduce the data into some smaller dimensional space. So computer scientists often think about this as just compression. We're just trying to take the data and make it smaller. But astronomers historically, and this is the sort of classic example from Joukowsky and Davis, are looking at the fundamental plane of galaxies here, how observable parameters of galaxies actually sit inside a smaller space, a subspace of the three-dimensional space being shown. And that there's a relationship between what's going on physically on the left side of the screen and what's going on observationally. So that was a real revelation and didn't require any labels, right? We're just thinking these three parameters, what is the space they sit in? And then we learn from that dimensionality reduction something physical. So it's an interesting situation where we're using a tool built really for dimensionality reduction just to compress data, but actually now we're learning something physical. So it's an interesting case of adaptation. Similarly, one could look at this nice paper by Portillo et al., where dimensionality of spectra were reduced and shown that the number of spectral components you need to classify a galaxy is only about 6. You could maybe do 7 or 8 or more, but the point is, using this variational autoencoder, which is a neural network approach, you can reduce the dimensionality of the space, and then you can see that broadline AGN and narrowline AGN, emission galaxies, coalescing galaxies sit in different pieces of this space. So again, it's first a way to ask the question, how big is this space? How much of the information in galaxies can we capture in 8 dimensions, in 9 dimensions, versus how simple it is. And so that manifold is really interesting until it gives you intuition about what's going on in the galaxies themselves. Clustering is another example. If you have some space, that space might not just be a smooth manifold, right? It might not just be continuous. It might have lumps in it. Here's a really nice example from Gravity Spy. They looked at these spectrograms coming off of LIGO. So this is a time on the y-axis and spectral on the x-axis, frequency on the x-axis. And what they did was very cool. They fed all of these glitches, these errors, into a community citizen science project. And people would sort of classify them into groups. They then took a neural network approach and asked, okay, if we took these classes and we fed in things that we couldn't classify, what would it do? They used a dimensionality reduction approach called t-SNE, and that's what you're seeing in the lower right. And what you can see is that there are still clusters in there. And these clusters are interesting. There are not very many objects in them. But by applying what had been done by the citizen scientists into a neural network, which we'll see is a very productive way of working, you can get these different clusters, which is very powerful. I'm going to take a brief comment on modality. I believe the universe is very weakly modal. I think there may be more objects that most of the people in this room could name that are in this room than there are in the universe. There are like my shoe is made of 600 weird little things that somebody has a name for that are all very specific, and there's not a continuous, there's no continuous range between the Flugelbinder and the eyelet or whatever. It's not like that. Whereas galaxies or stars, the main sequence is a sequence along mass. And yes, there are definitely different little blobs that we can see, but the universe is just extremely weakly modal. My usual line on the topic is, when you discover a new mode in astronomy, that's called tenure. When you discover a new mode in Facebook data, that's called Tuesday, right? There's not that much in terms of modalities. I believe there was a thesis done looking for variability in an early variability survey from about 10 years ago. And they took every single object and they classified everything, and they recovered all the existing modes of stellar variability and nothing new. So I think that's just very interesting. We got to remember that, because these tools are built for very modal human data, and our data is just not that modal. Okay, more cool stuff on supervised learning is outlier detection. This is a really nice and elegant approach. This is from a project. Oh, it has such a funny name. I can't remember, I'm sorry. But anyway, it's from EMU, where they did these very deep observations in the radio sky, and then used information theory to try to compress the images. And the idea is that if you look at the Shannon information, these are the sort of ones that are hardest to compress and therefore most interesting. And this is done just on an object by object level rather than on a group level. And that's, I think, a very cool thing. And it's an interesting way to get at these rare gems we've been talking about. I've elected to skip this next slide, but if you're interested in talking about text in astronomy or self-supervised learning, come talk to me or come talk to John. So don't have time to explain it. Okay, let's talk about supervised learning. So we've done a little bit of a tour of the difference between supervised and unsupervised, but I want to talk about supervised learning in astronomy because there's lots of cool examples. I think of this work as kind of the initial application that was most effective. This is called Real-Bogus, and this was basically looking for real transients. So when you're doing a transient survey, in the optical at least, you'll take an image, you'll get sort of a perfect background image, and then you'll take a new image each night, or however often your cadence is, you'll make a difference. And on the left are difference images of true objects, and on the right are bogus things. And so if you just say, I want something that's so bright, most of what you're going to get is junk. And so you need a system to deal with this. And the way this was done was, at the time, the best approach was not to work at the pixel level, but was to work, oh, right. So this is a system that is looking for the rare gems. The best approach was to make a feature vector set. So again, this is a 30-dimensional feature vector. And to translate for you, a feature vector is just a row. It's nothing else but a row. So you'd make a feature vector. So, the estimated uncertainty on the magnitude, the semi-major axis of the candidate, et cetera, et cetera. And then this was put into a big machine learning system. So this was put into a random forest classifier, which was very state-of-the-art at the time. Here it's classifying 4 categories of things. Here in Real-Bogus, there's only 2 categories, real and bogus. And you would take those different categories and do this random forest. So the idea essentially is you take a subset of your data, you create a tree, like a tree to separate the real from the bogus, and then you take another subset and you do this over and over again, and you combine all the trees into a forest, hence random forest, and you end up making some kind of classification system. And this was an incredibly powerful way to make these surveys go at speed. You cannot have a human look at every single time, a airplane went by or there was some glitch. Once again, the modalities here are being driven by humans. They're being driven by our telescopes and our stuff that creates all sorts of structure in the data. And those structures are really are often things we want to throw away. We're not so interested in deeply modeling every time the PSF is slightly out of focus or there was some airplane that went by. I mean, you can model that, but you have other things to do with your time. There's a lot of ranty interludes during this talk. SAS, I guess. So homoscedasticity is the idea that your error bars are all the same, okay? And the history of this is that way back, at the beginning of the last century, we worked with the statisticians to develop chi-square. And that was the sort of first time that we actually understood how to do heteroscedasticity, where the error bars are different, okay? But then, essentially, for the rest of the century, the statisticians got in bed with the economists, which, more power to them. Again, we need to understand economics. But if you ask, what's the error bar of the GDP of Kenya versus what's the error bar of the GDP of Iceland, they will just look at you like you're crazy. They don't think about those kinds of error bars. That's not a thing. Whereas with our data, there's really variable error bars, right? And we cannot throw away the low signal to noise data, and we can't throw away the high signal to noise data. There's information in both of them. And it took until 2010, 2005, that time frame, more than 100 years later, for us to be able to fit a line to data with covariant error bars in 2 dimensions. I mean, when I was in graduate school, we were doing wildly unprincipled things to solve this problem, which is crazy. Okay, so it just gives you a sense that the questions we're interested in aren't always the kinds of questions that our counterparts in statistics departments or in machine learning are interested in solving. So random forest existed in the mid-90s. Again, economics takes over. Let's serve better ads, right? That's the adage. And it took until 2017 for Dalia Baron and her collaborators to come up with a probabilistic random forest approach. Because of course, our sources aren't going to have some value. Essentially, you can't measure anything in astronomy unless you've measured its error bar. So again, if we're using machine learning, we've got to remember that it wasn't built for us and that we have to join those communities. So that's my takeaway point. Okay, let's do neural networks. So neural networks are actually pretty simple, asterisk. And I'll just do a very quick flow through of simple neural networks so we all know what we're on the same page about. So imagine you have some objects that have some mass and some energy. And what you're interested in is classifying them into 2 classes, so 2 different kinds of objects. So the first thing you do is you take your, remember, feature vector, rho, and you multiply it by some matrix. This is a matrix called W. It's 2 by 3. And the summation comes for free, because if you multiply a vector by a matrix, you get a vector out. Then the secret sauce, in some sense, one of the secret sauces of neural networks, is to apply some kind of nonlinear function. There's lots of nonlinear functions you can use. A very simple one is just pass the number right through, y equals x. If it's bigger than bigger than 0, or otherwise just pass through 0. That's called a ReLU. There's lots more complicated functions that might be better in different circumstances, but gives you a sense of how simple a nonlinear function you could use here. Then multiply by some other vector, by some other matrix. This would be a 3×2 matrix. Sum up, get some new vector, and then apply some kind of function at the end. And you can tell that, maybe low mass, low energy things are cats, but low mass, high mass, low energy things, or low mass, high energy things are dogs. Okay. So you would put in your dog that was, high mass, high energy, you'd feed it all the way through, and it would, because these networks are initialized, that W and that U, with random numbers, it's never going to do anything good. It's just going to give you 50-50 or just chaos. And the idea is that you change those parameters ever so slowly. Your network changes those parameters ever so slowly to update this to say, well, actually, no, I fed you a cat. So please make sure this network is more likely to return cat when I send this through again. And you send them through over and over and over and over and over and over and over again. You train this network up until the vectors you have, the matrices you have, W and U, are doing a good job. When you feed it something low mass, low energy, it feeds you back a cat. And when you, feed it one of these other things, it feeds you back a dog. Okay, it's a very silly example, I'll admit it. But it's important because it gives you a sense of how these networks work. When you start to want to work with images, that gets very hard because a deep neural network, you've probably heard of deep learning, that's what deep means, it might have many, many of these layers. And the number of input data you might need could be huge. Because if you have an image that's some reasonable size, say 100 pixels on the side, that means there's actually 100 times 100 input neurons. That's 10,000. And then you want to multiply that by numbers of layers. And we're starting to talk about enormous networks very quickly. You're trying to now minimize in a multi-billion dimensional space, which is very expensive. So we have to build smart architectures, often that obey the symmetries of the data that are going in. And I'm going to just talk about that briefly, because I want to just mention convolutional neural networks because they've been so important in astronomy, especially in the supervised learning world. So in this convolutional neural network, I'm just going to play a little video in a second. What you do is you put in your image and you convolve it with some kind of matrix. And the idea is that that matrix is actually a free parameter. So instead of doing what we normally do, well, I'm going to convolve it with a Gaussian, I'm going to convolve it with a Lorentzian, whatever. It's actually those are the free parameters. Those are the matrices. So this is sort of a somewhat old school convolutional neural network, but I like to show it. So I'm just showing you here, what you have on the input and these different convolutions. Those colors are the weights that connect. Then there's a downsampling because we can't run these networks. We need to make them small. So that's a downsampling called max pooling. Now we've got more convolutional layers. Again, those colors are the trained weights that let you go from your images to downsampled smaller images. Now you've got this max pooling, and this is called a fully connected layer. That's what we were showing before, where every neuron is connected to every other neuron. Those are expensive because you have to train every single one of those connections. And the idea here is that this thing now could recognize handwritten digits. So if I were to write the number 3, it would propagate all the way through. You see the different convolutional layers, and you can see that it's successfully found the number 3. Again, an interlude on image information. What's great and why I was drawn to machine learning to start with is that pixel-driven machine learning, like neural networks, can impose many fewer assumptions on where the information is. And I'll give you an example. You probably recognize these. Astronomers basically have 3 ways to look at the sky, as far as I can tell. One is black sky segmentation. The sky is black. There are things in the sky. Find the things, make a list. And then from that list, you can, measure the Sursic index, or you can measure the brightness or time domain or whatever, but it's a list. You're taking an image of the sky, you're going to a list. Great. Love it. Now, but wait, if I go back to the beginning of the universe, I've got this big sky thing. Let's use a power spectrum. So we can take the whole sky, we can run a power spectrum on it, and then, you can get lots of Nobel Prizes, and this is great if you want to understand cosmology. Or if you come from the interstellar medium, you might need something more complicated. And so you write some bespoke algorithm. This is work I did with a student 10 years ago, looking for linear features in data. Okay. And that's fine. But what ends up happening is, your algorithm is, going to think everything is a bunch of points. It's going to think everything is a Gaussian random field, or it's going to think everything is a filament. And these kinds of algorithms, if you just blindly apply them, will always tell you what you're looking for. So one of the powers of these neural network approaches is that they can actually work directly at the pixel and not tell you what you should be looking for. So here's some nice examples. CNNs can extract information from weak lensing maps. People working in weak lensing started from the perspective of CMB people looking at the power spectrum. But it turns out that after a redshift 1000, most of the information is not in the power spectrum, it's in the phase information. And in this case, it's actually in these little peaks, the peaks of the weak lensing. And so you can do much better if you use these more machine learning approaches that can show you where the information actually lies in the images. Another beautiful example from cosmology is work by Michelle Namaka, who is on the Science Organizing Committee. And what she's shown is that if you look at these simulated clusters of galaxies and you want to know things about them cosmologically, you do better if you exclude information about the cores of these images. And so understanding where the information is, in this case, it's in the outskirts of the images, not in the center, that's really critical. I think well, this is important for this crowd. Not only did networks not have to be in the abstract, they also don't have to be in the abstract. So you don't have to write machine learning papers. This is a paper written in 2018 by Schlafly et al. And the sort of key point here is that it took till page 4 for them to say, oh yeah, and we used a neural network to just do some dirty work for us, to sort out which algorithm we should use in which context. And that's what I'm showing here. And I think that's a really important thing, is that we often think about machine learning in the context of big surveys, in the context of looking for the rare gems. We think about it as like, oh, that's what I'm going to use for the last step, to go find the special thing. And that's fine, but it's also really useful for just pushing the system through. And I think that's a really important place to focus. Yeah, so there's the gem there. Okay, so I'm going to dive a little deeper on a particular topic near and dear to my heart, galaxy images. This is a lot of work that I've done when John Wu was in my group moons ago. Okay, so I'm going to use the galaxy brain meme. Let's classify these galaxies into morphologies so we can learn about their physics. This is something that we learned from our friend Edwin Hubble, among others. And here are these classes. Okay, that's cool. This is a compression, right? This is a way to compress the information from the images into something that we can sort, we can plot. Okay, fine. And Chris Lintott, you here, Chris? No, maybe? I know you're on the. Anyway, so Chris Lintott sort of took this to the next level, and he said, let's get citizen scientists to classify these galaxies into morphology so we can learn about their physics. Great. This was the original 6 classes that they used, looking at different shapes of galaxies from the Sloan Digital Sky Survey. Awesome. And that allows us to do things like study morphology the way we would study color, because we can have many people classifying them, and then we can say, how spiral is this galaxy? And this is a really nice diagram. On the x-axis is the density of galaxies, and on the y-axis is essentially, are they how much red spiral versus how much blue elliptical? Okay, which is sort of a funny thing because we mostly think of red ellipticals and blue spirals. And what this is showing that's very cool is that it's much more important. The thing that really governs when you go into a denser environment is, you shut off the star formation and you have many fewer blue galaxies and many more red galaxies. But you can still have spirals. You can still retain the morphology as you go into a deeper regime. Okay, and you can still have ellipticals far away. So really this separated the morphology and color as a function of density of galaxies. So that was a cool result that came out of this work. Let's take it to the next step. Let's train neural networks with data from citizen scientists to classify galaxies by their morphology so we can learn about their physics. Great. This, I think, is one of the most important papers that was ever written in astronomy and machine learning, because it really got us started. This is Dielman et al. And was sort of the starting gun. This was a Kaggle competition, and allowed it really showed that you could recover what humans were doing using neural networks. And I just love to show this diagram. That's Dielman et al, and that is neural networks in papers in astronomy literature. So you can really see the change happening. And then when we stop saying neural networks so often. But then we can skip all of this. Morphology has always been a crutch. There's tons of information that goes beyond morphological class. Morphological class is a fiction because there's a continuum, right? These are not actually, there's this an SBA galaxy and SBC galaxy. There's clearly a continuum between these things, and experts don't agree. So this is early work by John, where he showed by just looking at the images of galaxies, you could directly predict their metallicity. Okay, so that's telling you there's information in the images of these galaxies that predicts metallicity directly. And then we continue to take this forward. This is work, again, showing John's work here, where you could actually predict how much gas is in a galaxy. So this is, what is the 21 centimeter content of a galaxy in gas as a function of its image. I don't want to do too much details here, but the exciting thing about this is that John's here showing a method that allows you to know where in the image the neural network is looking. So that colorful thing that's on top in the plasma color is showing you which parts of the image the neural network is using to make its assessment that this is either a gas-rich galaxy, like in the top left, or a gas-poor galaxy, like in the bottom right. I think I'll skip this for simplicity, but we can cut to the chase. We can just predict the whole spectrum of the galaxy directly from imaging. And that's what this is. The red is the prediction, the black is the spectrum. You can see they sit on top of each other very nicely. So this is a really good example of showing us that there's so much information in our imaging surveys, and that we can use that to great effect to understand how galaxies work. This is just a funny story. There was our friend Bennett Hallwitter posted on Facebook, "Hey, does anybody have a spectrum of this galaxy?" And we said, "Well, no, but do you have a picture of it? Because we could get you a spectrum." So we did that, and John predicted this black line, which is the predicted spectrum of the galaxy. And then later we went to the archives. We found the places in the archives where the data were, and they confirmed the spectrum that we saw. And what's interesting here is that this galaxy is kind of an outlier. It's a very, very big galaxy. It's called Rubin's galaxy. And so there's a thought, oh, well, maybe it wouldn't fit because it's outside the training space. And in this case, it really did fit. And that was really, really cool. So this is a really nice example of where we actually showed that this wasn't a rare gem, that this is actually part of the surface of all galaxies. I'm going to skip showing off more of this stuff because I'm running a little late. So see John's talk tomorrow. But I will just say we're getting started here. This is, I just want to speak specifically to those of us who do optical ground and space-based surveys. These are the SDSS images. These are the legacy survey images. This is what you get for HyperSupremeChem, which is a pretty good proxy for what we'll see from LSST. Not perfect, but close. And this is what we get from Hubble. This is a pretty good proxy for Roman. There's so much information in these images. There's so much information to be mined. And right now, our surveys are not designed to think about all of this incredibly information dense detail. We're still in a mode of black sky segmentation, find me the orientation of these galaxies, extract a weak lensing signal. I don't care about these incredibly complicated nearby things. But there's so much information there that is untapped potential. So I'd say we're just getting started. I'll do some unsupervised learning in astronomy. The reason I think this is really important, why would we do this, is I think hypothesis generation in the big data era is an unsolved problem. Some of my best friends are theorists, and they are good people. And many of the things we do is they make theories and we test them, and that's great. But many of the advances in astronomy come from looking at the data and saying, that is a hypothesis generation, right? But I don't know how to do that with the 40 petabytes of LSST data or the 10 petabytes of Rubin data that I might be using. So if we don't create the hypotheses in the 2020s, there won't be an astronomy in the 2030s. So it's up to you guys to figure out how to come up with the hypotheses. We know how to do hypothesis testing, just not hypothesis generation. Finding the weirdest galaxies in Sloan spectra is a beautiful example of this. This is work by Barone and Poznansky. They are basically doing this thing where they take all the spectra from Sloan, from the main galaxy survey, they run random forest to find how often things are in the same leaf, and they use that information to create a weirdness score. So they find 400 very weird galaxies from Sloan. And then what Dalia Baron did for her thesis is to follow up a very small set of these, which were E plus A galaxies that have AGN lines, and looked at them with KCWI on Keck, and showed that in many cases you could see these winds in 3D blowing these galaxies apart. That the AGN winds were actually showing you this rare thing, the caught in the act thing astronomers always talk about, of a rare transition moment going from a star-forming galaxy to a red and dead galaxy. So this really informed how we think about galaxy evolution. But I just want to point this out. Since they wrote this paper on the 400 weirdest galaxies in Sloan, there have been an extraordinarily few number of studies on those weird galaxies. We don't know what to do when we find the rare gems. This is a website called galaxyportal.space. As far as I know, it's still up. You can go check it. It's a beautiful interactive tool that allows you to explore all these galaxies and their weirdness score against every conceivable feature that you might want to see. And I'm sure there are galaxy experts in this room, and I doubt that they have looked at this website. So what is it that we're doing culturally or not doing culturally to allow ourselves to find these things? Just want to point out that finding things, the gems aren't necessarily objects. Sometimes they're gaps. I love this one. This is the Jiao Gaia gap. It's a gap in the main sequence. So that's stars, and you can see this little slice. John Debus still owes me a bottle of whiskey because he thought this was an artifact in the data, and I knew that it was real. And it has to do with transitions and stars that I don't care anything about, but I'm very excited about it. And I pointed out this thing, this is a one-dimensional gap in the most famous second most famous two-dimensional space in all of astronomy. The most famous two-dimensional space is the sky, but the second most is the color magnitude diagram. And so this is a one-dimensional gap, and it was found by eye. What happens when we have a 17-dimensional space with an 11-dimensional gap in it? Are we ever going to find that? Gabriel Contardo, who does algebraic topology, heard me rant about this and came up with a solution, and that's what you're seeing on the right here, a way to find gaps in point-like data. It still needs lots of work, but it's a really cool idea, and it's an example of the kind of thing that we're not going to be able to find, and the kind of hypothesis we want to be able to generate from these data that we're building, but we don't know how to do it yet. I want to give a word of caution. Machine learning can send you down weird rabbit holes if you're not careful. This is a paper by a postdoc who was working in my group at the time, looking at some previous work that had done some clustering to find these so-called stellar strings. And we saw by looking at them, they're just not real. This was clustering done by ML and by I, and it's just incorrect. And it's been cited hundreds of times in the literature without looking at the actual process. So we have to be really careful. Astronomers are sensitive to this. Because we really do think that there's a deep connection between neural networks and black boxes. This is from SciAx. So I just want to be careful. We need to use these tools to find new and exciting things, and that's exactly what was being attempted here. But we also have to be very skeptical in the most positive sense of that term. And I think I'm over. So I think I will not do the last point, search by image. But I think I'll just say out loud that the overall idea is that one thing we'll want to be able to do in the future is to look through these data and to be able to search them not just by metadata and not just by the parameters, their Sirsic index or their color or what have you, some time domain signature, but we'd actually like to be able to search by the image or even by the time domain information. We like to put something in and say, do you have more things like this? And we don't have that capability yet. So I'm going to skip this section and do that really sneaky thing where I do this bit. I'll go to my conclusions. So conclusions. Machine learning is a popular and powerful tool for astronomy, but it's not a replacement for statistics. Please, if you have a statistical model that's powerful and you can run it. We need to join ML experts to develop tools appropriate for our problems. We can't just use off-the-shelf tools. It's a great place to start. We've gone from morphological classification to true physical analyses, and we're just getting started. This is such an exciting part for me, seeing data that's about to be coming from LSST, from Euclid, from Roman. I put to you that hypothesis generation is not a solved problem yet in this big data era, and I think this is the team to figure it out. So please figure it out. I'd like to have a job in the 2030s and 40s. And then we are going to be needing to build tools cross industry, cross science to do astroinformatics in the 2020s. And I'll leave it there. Thank you.